Imagine looking up at the night sky and seeing something that shouldn't be there. Not a planet, not a comet, but an invisible cosmic giant, a rogue black hole. The universe is a messy place. We often think of our solar system as a peaceful clockwork mechanism held together by the gentle, massive hand of the sun. But what if that hand was replaced? What if, instead of a sudden, fiery cataclysm, the end of our world came in slow motion? This isn't a scenario where the black hole zips through at the speed of light, swallowing everything instantly. That kind of event is rare and quick. We're talking about the slow-motion apocalypse, the nightmare scenario where a stellar mass black hole, maybe 3 to 10 times the mass of our own sun, wanders in from the galactic void, moving at a relatively glacial pace, perhaps just a few kilometers per second, slow enough to become a gravitational anchor for a terrifying amount of time. This rogue object, let's call it the Wanderer, isn't the kind of supermassive behemoth found at the center of galaxies. It's the ghost of a giant star, collapsed and invisible, but still wielding its colossal gravity. The first sign of the Wanderer wouldn't be a dramatic explosion or a tear in the sky. It would be a subtle, creeping chaos starting at the very edges of our domain. The Oort Cloud. The Oort Cloud is a vast, icy shell, billions of kilometers from the sun, where trillions of comets reside. Our sun's gravity barely holds it. When the Wanderer, moving slowly, gets within a light year or two, its gravity begins to tug. This is the first sign of disruption, the cosmic alarm bell no one can hear. Comets, perturbed by the new gravitational bully, would be flung in 2 directions. Some are ejected entirely from the solar system, lost forever, but a terrifying number are aimed inward towards the planetary zone. The show begins years, maybe decades, before the black hole itself reaches the Kuiper Belt. We'd see an unprecedented storm of comets, a celestial shooting gallery far worse than any meteor shower. Life on Earth would become a constant gamble against multi-kilometer-wide icy missiles. This bombardment is the prelude to doom. As the Wanderer gets closer, passing the orbits of Pluto and the Kuiper Belt, the delicate billion-year-old orbital stability of the solar system starts to crumble. The black hole's mass is comparable to the sun, meaning we now have 2 dominant centers of gravity. The planets, once loyal servants of the sun, are suddenly caught in a chaotic 3-body dance. The first planetary giants to feel the squeeze are Neptune and Uranus. Their orbits, which have remained stable for eons, begin to stretch, warp, and precess wildly. Tectonic forces on these ice giants would go haywire due to the changing tidal stresses. As the Wanderer gets closer, the effect on Jupiter and Saturn is even more profound. These gas giants are the heavyweights of our system, and their stable, massive presence usually acts as a shield, deflecting wayward comets and asteroids. But now they too are jostled. The black hole, still hundreds of astronomical units, AU, away, starts pulling and stretching them. Jupiter's great red spot might even undergo unpredictable changes as the massive planet responds to the wildly fluctuating tidal forces. More critically, the rings of Saturn, that breathtaking feature, are likely to be violently disrupted. Tidal forces from the Wanderer would stretch, compress, and ultimately scatter the fine ice particles, creating temporary, breathtaking spirals before the rings are potentially torn into a broad, diffuse mess, or even partially captured by the black hole itself. But the real drama begins when the Wanderer crosses the Asteroid Belt, the boundary between the gas giants and the inner rocky worlds. The Asteroid Belt is a graveyard of rocky debris, usually held in a relatively stable orbit. The black hole's gravitational field, acting like a giant invisible plow, would catastrophically destabilize this belt. Asteroids would be flung in every conceivable direction, outwards, inwards, and perhaps most terrifyingly, into highly elliptical orbits that cross the paths of Earth, Mars, and Venus. Suddenly, the inner solar system isn't just dealing with a few extra comets. It's facing an unprecedented perpetual meteor storm of rocky and metallic projectiles, some the size of small cities. This period could last for centuries, depending on the black hole's speed. Every moment on Earth would become a literal game of celestial Russian roulette. Now, let's talk about Earth's orbit. Our year is currently defined by a near-perfect, slightly elliptical path around the Sun. When the wanderer gets within, say, 10 AU, roughly Jupiter's orbit, the gravitational pull from the black hole becomes a major, unpredictable factor. Our orbit would cease to be a neat ellipse and would begin to resemble a spaghetti strand in 3 dimensions. We could face several immediate catastrophic scenarios. Extreme eccentricity. Earth's orbit stretches dramatically. We might swing out to a distance where water freezes solid and the atmosphere partially collapses, a global freezer, only to then swing dangerously close to the Sun, boiling the oceans and scouring the surface, a global oven. Life would cycle between impossible extremes. Orbital tilt. The Earth's tilt, which gives us seasons, would become wildly unstable. Imagine the poles suddenly facing the Sun directly for years at a time. Capture into a binary system. The worst-case scenario. Earth gets pulled out of the Sun's stable orbit and begins orbiting the wanderer instead. If the Earth is captured by the black hole, the light and heat from our Sun would become a distant, tiny star. Temperatures would plummet instantly. Surface temperatures would drop to absolute zero, and the oceans, atmosphere, and even the air we breathe would freeze solid in a matter of weeks or months. This is the true global winter. But perhaps the most immediate and horrifying disaster is tidal heating. A black hole, even one far from Earth, still has a massive gravitational gradient. As Earth orbits the wanderer or simply passes close to it, the intense, non-uniform gravitational pull would constantly stretch and compress our planet. Imagine a giant squeezing a tennis ball over and over. This friction and flexing would generate enormous internal heat. Tectonic plates would grind and rupture with unprecedented force, causing global-scale super-earthquakes. The Earth's core would heat up, resulting in extreme volcanism, not just isolated eruptions, but fissure eruptions covering vast areas, pumping massive amounts of greenhouse gases and ash into the atmosphere. The surface would become a raging inferno, a geological nightmare where the ground itself is constantly unstable. This tidal heating could be the ultimate extinction event, heating the Earth from the inside out, long before the planet is swallowed or frozen. Now, let's consider the Sun itself. The Sun is a powerhouse, but it's not immune to gravitational interference. If the wanderer passes relatively close, say within a few hundred AU, it will begin to strip material from the Sun's outer layers. While a stellar mass black hole won't consume the entire star, it will create massive, unpredictable solar flares and coronal mass ejections, CMEs. These CMEs would be far more intense than anything we currently experience. When they hit Earth, they would scour the ozone layer, causing fatal radiation levels, and completely wipe out the global electrical grid. Satellites would be destroyed, and any remaining hope for long-distance communication and coordination would vanish. Civilization, already battered by climate chaos and asteroid impacts, would be plunged into a global dark age. If the wanderer passes very close to the Sun, say within 50 AU, the Sun's fusion core itself could be temporarily perturbed. The sudden change in gravity could alter the pressure balance, potentially leading to a temporary increase or decrease in solar output, exacerbating the temperature swings on Earth. What about the long-term fate of the solar system after this slow passage? Assuming the wanderer doesn't directly swallow the sun or the major planets, its slow departure leaves behind an utterly unrecognizable system. The beautiful, stable, and predictable orbits of our 8 planets and the countless minor bodies are replaced by a gravitational free-for-all. The orbits that remain will be highly inclined and extremely elliptical. For example, Mars might now orbit the Sun at a massive tilt, and Venus might have been ejected entirely. The gravitational potential energy of the solar system will have been dramatically rearranged. The once tidy plane of the ecliptic, where all the planets orbit roughly in a disk, will be gone. Imagine a giant pinball machine. That's our solar system now. For any remaining planets, the new normal is perpetual orbital instability. It's a matter of time, perhaps millions of years, before the next major gravitational interaction, a planetary collision, a planet being flung into the sun, or a planet being ejected into the cold interstellar space. Now, let's return to the worst-case scenario. The Earth is pulled directly into the black hole. If the wanderer passes close enough, the tidal forces are the final, inescapable destroyer. As the Earth approaches the event horizon, the point of no return, the difference in gravitational pull between the near side and the far side of the planet becomes astronomically vast. This process is called spaghettification. The side of the Earth closer to the black hole is pulled much harder than the side farther away. The entire planet is stretched and compressed into a long, thin strand of superheated, shredded matter, resembling a piece of spaghetti. Rock, oceans, atmosphere, and everything on it is ripped apart at the molecular level, compressed into plasma, and accelerated towards the singularity. The matter doesn't just disappear, it forms an accretion disk, a swirling, superhot disk of pulverized planetary material around the black hole. This disk, heated to millions of degrees by friction, would emit incredibly bright and lethal X-rays and gamma rays. For any other surviving planets, this accretion disk would temporarily turn the wanderer into a brilliantly shining Death Star, bathing the remaining solar system in deadly radiation. If by some slim chance the black hole merely grazes the sun and leaves the inner solar system, with Earth still intact but in a highly elliptical orbit, what does the planet look like? It is a hellish, unrecognizable wasteland. The atmosphere is scoured by CMEs. The surface is pockmarked by impacts from the now scattered asteroid belt. The oceans are either completely vaporized during the close solar passes or frozen solid during the distant freezing swings. Any remaining life would be relegated to deep-sea hydrothermal vents or protected subterranean refugees, essentially starting evolution all over again in the most extreme volatile environment imaginable. The nature of rebirth and evolution after the catastrophe. In the grand, terrifying what-if of the black hole's visit, the most fascinating scientific question lies not in the destruction, but in the potential for bizarre new life and the cosmic resilience of nature. If Earth survives, even as a desolate ruin with a radically altered orbit, the engine of life might still be sputtering. Extremophiles, organisms thriving in impossible conditions, could inherit the shattered world. Imagine life evolving under 2 suns. If Earth is captured by the black hole, using the black hole's accretion disk as a short-lived heat source and the sun as a distant light, or life adapting to years-long periods of darkness and extreme cold, followed by brief, scorching summers. Deep-sea vents, shielded from surface chaos, would become evolutionary islands, potentially giving rise to organisms that rely solely on geothermal energy and chemosynthesis, utterly independent of the sun. However, the final, most astounding fact about this scenario is the black hole's own stealth. If the wanderer is not surrounded by an accretion disk, it would be completely invisible. You can't see a black hole directly. You only see its effect on light or matter. This means that depending on its approach angle and speed, the black hole might not be discovered until its gravitational influence is already irrevocably scrambling the inner solar system. Advanced surveys like the Vera-C-Rubin Observatory would be our best hope, but even then, finding a small rogue black hole hundreds of AU away is like finding a needle in the galactic haystack. We would likely detect the gravitational lensing, the distortion of light from distant stars as it passes around the black hole, or the sudden massive chaos in the Oort Cloud first. The most shocking scientific realization: we might not have the luxury of a decades-long warning. If a stellar mass black hole approached from an unfavorable direction, far from our current observation plane, the first sign of its existence might be the impossible, destabilizing wobble of Jupiter's orbit, signaling that the cosmic clockwork has already been irreparably broken. That is the true silent terror of a black hole wandering into our celestial backyard, an invisible, inevitable force that replaces the gentle pull of our sun with an untamed, apocalyptic gravity.